The central struggle of modern electric vehicle engineering comes down to a single physical problem: cramming massive power through shrinking spaces without melting the hardware. For decades, the workhorse of power electronics has been the silicon insulated gate bipolar transistor. It is the switch that made early electric vehicle inverters possible. But silicon has a strict physical ceiling. Its switching frequency is capped at roughly 20 kilohertz. Try to switch it any faster, and the thermal switching losses become so extreme that the chip will melt. To break this limit, engineers turn to a third-generation semiconductor material, silicon carbide, or SiC. The defining physical feature of silicon carbide is a band gap 3 times wider than standard silicon. That wider band gap translates directly to a massive increase in breakdown field strength. It allows silicon carbide transistors to switch up to 10 times faster than their silicon predecessors. This schematic maps out exactly where these upgrades are deployed in an electric vehicle. You can see the specific applications outlined in blue: the main traction inverter, the DC-DC converter, and the onboard charger. Silicon carbide is a mandatory architectural shift. Hitting 98% inverter efficiency and enabling 800-volt hyperfast charging platforms requires this exact material. However, replacing an old silicon switch with a faster silicon carbide switch in a legacy inverter architecture causes the system to violently tear itself apart. This flowchart maps silicon carbide's challenges. Top tier: extreme speeds generate massive voltage and current spikes, causing electromagnetic interference. Middle tier: this noise triggers crosstalk, causing erratic switching and weaker short-circuit ruggedness. Bottom tier: transients travel downstream, causing motor isolation failures and destructive bearing currents. The silicon carbide chips themselves are highly mature and stable. The problem lies in the legacy automotive architecture surrounding them. Each was never designed to handle these operating frequencies. Treating silicon carbide as a simple drop-in replacement is an engineering dead end that leads directly to catastrophic hardware failure. These system failures aren't caused by a chemical defect in the semiconductor. They are the result of a violent clash with a 200-year-old law of fundamental physics that weaponizes the inverter's own wiring against it. To understand why the hardware breaks, we must look to the foundational rules of electromagnetism, discovered by Michael Faraday and Joseph Henry in the 1830s. They defined the law of self-inductance. When a changing electrical current moves through a conductor, it induces a countervoltage that actively opposes that exact change in current. The induced voltage, E, equals negative inductance, L, times the change in current over time, dI over dt. Faster current changes cause larger spikes. Legacy silicon IGBTs switch slowly, meaning dt is large, keeping the voltage spike small. But silicon carbide switches 10 times faster, shrinking dt. Dividing by this tiny number causes E to violently expand, generating a massive destructive spike. This abstract math has immediate physical consequences inside a semiconductor module. The L in the formula, the physical inductance, comes from the microscopic wire bonds used to connect the silicon chips to the module housing. The massive voltage spikes generated across these tiny wires induce phantom signals. This creates crosstalk, which forces neighboring transistors in the bridge circuit to turn on unpredictably, creating catastrophic short circuits. Silicon carbide is uniquely vulnerable here. Its gate oxide layer is physically thinner than standard silicon, making it highly susceptible to defect breakdown when hit with these extreme transient voltages. Silicon carbide's greatest physical advantage, its blinding switching speed, mathematically guarantees electrical self-destruction if the physical inductance of the circuit is not heavily mitigated. The voltage spikes are only half the problem. Silicon carbide also triggers a secondary crisis: extreme thermal density. Because SiC materials can handle massive voltages, engineers shrink the physical chip, moving from a 98 square millimeter silicon footprint down to a highly concentrated 26 square millimeter area. This chart shows heat exchanger thermal resistance. Wolfspeed CIC modules are blue and green, compared to the larger Infineon silicon IGBT in red. Following the practical thermal limit curve upwards, as die area decreases, thermal resistance spikes. The concentrated heat from smaller CIC dies overwhelms standard aluminum heat exchangers. While the inverter struggles to cool, high-frequency electrical noise travels out, moving directly into the traction motor. Inside the motor, these rapid voltage pulses cause partial electrical discharge between the copper windings. Over time, this physically degrades the motor's internal insulation. Even worse, the high-frequency common mode voltage from the inverter creates a parasitic capacitive coupling effect. This induces a dangerous high-frequency voltage directly on the spinning rotor shaft. This shaft voltage violently searches for ground. It arcs directly through the thin oil film of the motor bearings, creating destructive microcraters in the steel. In legacy systems, the silicon carbide powertrain faces a terminal failure loop. Concentrated heat overwhelms cooling, while high-frequency transients electrically machine the motor bearings to death. Surviving these forces requires returning to the induction formula, E equals -L times dI over dt. We cannot lower the current because electric vehicles demand high power, and we refuse to slow down the switching speed because we demand high efficiency. The only mathematical path to survival is to physically engineer the L, the parasitic inductance, completely out of the physical module system. The primary physical battleground for reducing this inductance is advanced semiconductor packaging. Engineers are abandoning legacy planar packaging. They are stripping out the problematic wire bonds entirely in favor of wire bondless, flip-chip modules designed with tight, three-dimensional vertical power loops. This geometric redesign has a massive impact. By shortening the physical circuit paths, parasitic inductance plummets from 15 nanohenries down to less than 5, mathematically flattening out the destructive voltage spikes. In the era of silicon carbide, physical geometry and proximity of connections are just as critical to performance as the semiconductor's chemistry itself. Beyond packaging, engineers deploy active algorithmic circuit-level interventions to tame the raw speed of the material. They use an engineering technique called soft switching. Soft switching completely eliminates the overlap of voltage and current transients during the exact microsecond the transistor turns on or off. This diagram shows a highly effective soft switching topology called the Auxiliary Resonant Commutated Pole Inverter, or ARCPI. The LC resonant circuit acts as an electromagnetic shock absorber. It allows the main switches to achieve zero-voltage switching, effectively killing the destructive ringing effect inside the module. The final layer of control is the multi-stage voltage gate driver. The schematic shows how it actively shapes the electrical signal. A parallel array of internal switches allows the driver to granularly control the exact rise and fall time of the gate voltage. This multi-stage approach allows the vehicle's computer to dynamically throttle the silicon carbide switching speed. It actively adjusts to changing loads to prevent overshoot before it happens. Harnessing silicon carbide requires a total ecosystem redesign, from microscopic chip packaging to macro-level circuit topology. This comprehensive overhaul ultimately forges the resilient, hyper-efficient foundation of the 800-volt electrified future.